Thanks, Peter, for the kind introduction, and thanks for being a presenter here and for the honor to present the Tinker project in, as you said, four different presentations or an own slot. So I will be starting off basically with providing you all a small overview about the project and some slight insights where we are at the moment in the project. But first things first, who are we? So not in case of Tinker, but in case of Profactor. So I'm from Profactor. It's a small research company in Upper Austria, in Steyr, in Austria. We are there since 1995. We have also another department in Vienna, a small one. We are around 75 people, and here I said some hard facts on that. So what we are dealing with, our main two fields of research are in industrial assistive systems or assistance systems and additive micro nano fabrication. To keep it short, I'm from the additive micro nano fabrication, actually the head of the respective group, and we are dealing also in a little bit smaller or fragmented way, would say, with nano and microstructures and functional surfaces. So nano imprinting, lithography, and inkjet printing are our main technologies behind that, where our research is basically all based on. But so much for Profactor. Today's topic is indeed all about Tinker. So let's talk about Tinker. The motivation of this project, as Peter briefly introduced, is on autonomous driving, on the ADAS systems that are all sorts of dealing with sensors in cars. So maybe you are familiar, maybe not, but just a broad overview, there are tons of sensors incorporated into a car that can track the surrounding. Also considering, let's say, certain developments, not just assistive systems, but indeed going for self-driving cars. There are a lot of radar, LiDARs, short range, long range radars, cameras, and so on that are capable of tracking the surrounding. So, but with all these sensors having in mind, or let's talk first about the levels of autonomous driving. There is a certain, let's say, categorization, how much independent a car can act on its own. So from human to machine about the responsibility. And I'm leaning on some pop culture references here that you can consider what is the actual level. Like, for example, you know, Herbie out of the 60s, 70s Disney movies. He's driving basically on its own, but it's a relatively older, relatively robust. But yeah, technology-wise, in the 80s, we got slightly improvement. Also, let's say in the design, and the car was able to talk to one. But the driver, Michael Knight, was able to drive the car without having actually driving the car. So Kit was driving on its own. More recently, or not even recently, it's also already about 10 years ago, iRobot, the movie where this was quite the opposite around, where in this scene, for example, the co-pilot, so to say, was strangely reacting, "Hey, what are you doing?" And Will Smith was actually then driving with his own hands, so the car was already fully automated. But the driver was able to interfere, although in this movie not recommended. And yeah, there are also completely self-driving cars, maybe self-aware cars, maybe in a distant future, I don't know. So these are just some let's say, some impressions. But sorry for being this news article in German, but I will translate it to you that, for example, this year, in the beginning of the year, this Tesla self-driving modus, which was promoted quite heavily, was actually not suited for indeed autonomous driving, which was kind of what's happening there. So the promotion and the actual capabilities were not, or let's say they were a little bit too ambitious about that in the beginning, but we're, let's say, between level 2 and 3 kind of. So what's the motivation indeed of Tinker with this small exercise before? So the need for indeed self-driving cars is they are currently consuming relatively high power. As said, tons of sensors are included, so you need a lot of power. There is a lot of power consumption, meaning that this needs to be lowered. Also, tons of sensors, meaning tons of weights. Which is in automotive industry quite of the painkiller if it gets, or not painkiller, deal breaker, if you think about it, and also reliability and so on and so forth. But this is what we want to, or what we saw in the project in the beginning. So there is indeed a high market need also regarding, let's say, standards. There is also a driver regarding standards between this 24 gigahertz standard regarding the traffic telematics, which is changed to 77 gigahertz. So there is a driver to improve that, and all along comes with miniaturization to deal with that. Miniaturization would therefore dictate smaller weight, smaller power consumption, and so on. So this would be the main, or hopefully one of the main solutions in there. So what we set as our goals in Tinker, there are mainly two goals that can be compiled. One is the manufacturing of such radar and LiDAR sensors for autonomous driving for automotive industry. And by how we want to do that is by setting up a specialized Tinker pilot platform comprising of several elements. I will come to in a minute on a more detailed level, but all addressing improving miniaturization level, improving functionality, improving efficient use of resources, liability, and also lowering the rejection rates, which was, as it is a Horizon Europe project, out of the topic text, we wanted to address quite logically out of that to have more dedicated use of resources. Here, maybe a better depiction of what we are saying is that what the pilot platform is capable of. You have on the one hand assembly of via pick and place and bonding technologies, dealing with assembling bare die chips into a certain package, into a certain PCB or whatsoever, together with additive manufacturing to actually build, let's say, functional structures for radar and LiDAR sensors, realized mainly by inkjet printing and nano imprinting technology. Therefore, here comes the whole 3D printed electronics part into it. The glue that fits things together and also dealing with the rejection rates is the feedback control, meaning that we have a certain inline inspection that is triggering an inline compensation to have a full feedback control to lower the rejection rates, to do a more dedicated fabrication. So how we achieve our goals? More detailed on the additive manufacturing side. As said, we are focusing here on inkjet printing and nano imprinting lithography to a dedicated process development, but not just that. So when considering additive manufacturing, and I think today we heard it already, I think by Ralph it was, that the materials are the most critical part in additive manufacturing. So we have a material development within the project. More on that on my colleague or my brother in arms, so to say, in Tinker, you hear later. We have also some applications considered, like what for we are doing that, like the direct integration of sensors assisted by additive manufacturing, PCB manufacturing, and so on and so forth. let me show you a glimpse into what we are currently. So it's not just, let's say, a promotion talk now of the Tinker project. I wanted to also give some glimpses into what we are facing at the moment. And since the project is running for 1 year, so you can expect that there is a lot of progress. Like, for example, partner EV Group, or short EVG, set up or adapted a pilot line part for the project that is dealing with nano imprinting. We also, on Profactor side, established some imprinting tools for replication of nanostructures. Here, a short glimpse of some latest achievements. More to come in the next month, I would say. On material side, you will hear in this session also from Hanan on our material developments, on the inkjet printer pilot part, or a glimpse into that from David Falk from Notion Systems, and right after my talk, some application side from the radar part of the project. So stay tuned right after my talk. About the feedback control, as said, this is the glue that puts two things together. We are focusing, as said, on the inline inspection, and if you think of or consider that an auto repair mechanism is incorporated in the project, of course there is an AI involved in machine learning to identify what can happen in the machines. So optical inspection, data processing is there, feeding into this zero defect manufacturing, zero waste, low rejection rates objective. Where are we currently? So one of these challenges is that during a placement or during one of the assembly steps, assembling a chip into a certain PCB cavity, wherever, there might happen that there is a certain gap that needs to be treated in order to continue with the fabrication that comes afterwards in assembling the whole stuff together. And one critical part here is indeed to, and having this zero defect or this low rejection rates consideration is, this is considered as an error, and this needs to be compensated by one of the toolings of the pilot line. So here is a short insight about the actual image that is being used, and the data image that is then processed out of it, that is then being used for within the same machine, respectively in a follow-up process step. Last but not least, the assembly part. So as said before, the inline inspection is key to align the certain bare die insection, meaning here the goal especially here is on accuracy, that the bare die chips, respectively the packaged sensors, are placed correctly. And here again the glue fits everything together and helps combining everything together. Also, prediction is here considered, that the machine learns by itself and corrects itself. Again, some small glimpse into where we are standing currently. Here you see an example of a mock-up of a test sample that's being used for process development, where in a model PCB, a chip is assembled into it using the data domain machine from partner BESI, and having the respective images for autocorrection for the machine learning part to correct that is being used. What I still left out actually is also some facts on the project itself. As said before, it's an EC-funded project. It started last year, so we have our annual meeting also online in this crazy COVID times, but we are looking also forward to actually first meet in person. So this is some small insight that we never met in person actually, crazy times. But the consortium, nevertheless, comprises of quite some key industrial players in this field. And we have, of course, some online presence. So feel free to look into our webpage, on our LinkedIn page, and also on Twitter. Last but not least, I want to provide you a small outlook what is coming ahead. So right in December, stay tuned on our website, on the LinkedIn group or LinkedIn page. There will be some public information coming up regarding process and material development in the next month. Also in 2022, it's expected, according to the work plan, that you will hear from us about the operational pilot line and also about some prototype manufacturing. And in 2023, we are closing the project, hopefully with a nice demonstration and so on. If you need some more information on that or want to get in contact with us, feel free to contact me or my sister-in-arms from Amires, Martina Chopard, who is the Dissemination and Exploitation Manager. Thank you.